first to thank the organizers for this opportunity to speak here. So I will report about the work which is done together with Georg Schwitter. Last years I have some privilege to work with this very talented young series. And first part of our work was published 2 years ago. Some extended version is on archive, and now there is some continuation. And meanwhile, there was alternative derivation of what I will present here in this book. Okay, so it is motivated by experiment where just people try to demonstrate the visualization of Anderson localization. I will give some few slides about how it is done. And it is two systems. One is in photonic and the other one in Bose-Einstein condensate. So what we did is we studied a classical equation which supposed to describe this two systems, non-linear Schrödinger equation and Gross-Pitayevsky. And for this classical equation, we developed some effective theory of a pulse which is propagating in non-linear and disordered medium. And this equation, which was found, appeared to contain some curious phenomena, which can be called some local explosion and diffusive collapse. I will explain what it is about. And in the end, I will discuss a continuation of all that, about the role of collision in this equation and about collision integral. So experiment is looking like that. So here it is how it is done in the Bose-Einstein condensate. Namely, if maybe you can see this vague paraboloid. This is magnetic trap where initially boson atoms are confined, and then it is released. And here it is one-dimensional realization of one-dimensional disordered potential, and particles just released from this trap trying to expand. And they study under many just repeating of this measurement what is the time of evolution. And here it is, you see these tails manifest dependence on the distance, manifest localization. And depending on the strength of disorder, in case of no disorder, this green line is just ballistic expansion. In case of moderate disorder, you have seen this initially this parabolic motion, but then after some time one can observe saturation, and this saturation manifests itself that system is in the regime of Anderson localization. So that is an attempt to demonstrate visually effect of Anderson localization. And even before that, there was similar attempt in photonic. The most invention was demonstrated here, the circle with this 3 points. That is this invention of the authors of this paper. Shmuel Fishman is here. He is one of the co-authors, so all questions to him. And what is here is the use of Kerr effect for the photonic crystal. Now, in this three-dimensional system, one direction becomes time. This, let's call that, appeared effectively time. And they study how this wave packet being just injected on one side, propagates and recorded the output on the opposite side. So then what one can see is that, so on the opposite side of the photonic crystal, what is recorded is looking rather weird, but if one takes the log of that and average, then this parabolic behavior is diffusion, and this linear is tails of Anderson localization. And you see, so for this is the level of disorder. For moderate disorder, you have diffusion, and for the strong disorder, this localization. And again, unlike previous measurement, one cannot record the full evolution, only what is on the opposite side of the crystal, so at a given time. So one cannot, unfortunately, do this kind of measurement. Okay, and also they measure effect of non-linearity, how the non-linearity influence all that, and one can see that indeed non-linearity, this index alpha just is a strength of non-linearity. The more non-linear system, the more strong effect of localization. It is not that I say that I understand what is going on here, because if this one is relative strength of disorder, and that is the what is supposed to be radius of this spot, which may be treated as some radius of localization. Pay attention on this offset, so you have more or less relatively weak dependence on disorder. So all that is actually, despite that it is some broad scale, is actually just done in the limit of relatively strong disorder. And the intermediate regime, which is supposed to be somewhere there, is not covered at all. Okay, so now come back to series, so two systems, and they are described by identical equation. Here, for the photonic one, as I say, the direction along this direction of propagation is effectively time, and what is in other two directions, it is space. So the new term is this one, which is the random disorder, and nonlinear term is here. And in physics of Bose called atoms, that the nonlinearity is because of interaction, and relation between this nonlinearity and the scattering length is here. And in physics of photonic crystals, that is Kerr effect, which is the origin of nonlinearity. And typically, for Bose for cold atoms, you have repulsion, and for here, for photonics, you have attraction. Okay, so from our point of view, we have injected something. Here it is some disordered profile. Very interesting what to do with that. Now, first of all, even when without nonlinearity, that is very different from what we usually have in condensed matter in case of electrons, because there you mostly narrow in some region of energies, while here this wave packet which is injected, it has some distribution of energy. And if you even take just ordinary diffusion and average, and its propagation depends on the diffusion coefficient, which in turn depends on the energy. And if you average this kind of just output for the density, how it's evolved in time, and take some reasonable example of distribution in energy, then one will get something which is also have linear just tails in the exponent, as if it is localization, which is not, because this x naught is something which depends on time, which in case of photonic system one cannot change. Okay, so if one look what kind of process we are discussing, this is line just manifestation of nonlinearity. That is our propagation. This vertical line symbolically tells us what happened in the initial moment, so that is injection. This kind of thing is telling us how wave packets propagate along the different trajectories, then just because of nonlinearity it starts influence further on propagation until somewhere here there is the point in space and time where density can be recorded. So important issue is that here, unlike what you have in case of the just quantum systems, true ones, there are no loops just because it is classical equation. So all what may happen in the system is what was initially injected and after that propagated, but you don't have background which may fluctuate. So because of that, typical kind of contributions which you have is very different from what we have in case of the disordered electrons, which are usually we have in mind that there is some fermacy, and this fermacy have some quantum fluctuation, and this fluctuation in the presence of disorder provide main effect. Here, nothing like that, so we may mostly have this kind of picture that something is diffusing and influence diffusion of the rest of, and the rest is also the same in wave packet. And the question is how to describe it. So there are two kind of processes. One is exchange of the momentum during this nonlinearity, and the other one is exchanging of energy. So because of that, so and result is that effective kinetic equation which one can derive in this case is that one. So you have some diffusion which depend on the effective potential which is created by nonlinearity. So one sees that it is nonlinear equation because this potential itself depends on the density. Density is actually integral of this distribution function in energy over energy. So it appears through all these nonlinearities, and that is what is initially injected. And what I say about this derivative and so on is just this term is responsible for this change of the energy, and that one is responsible for that one. You see it stand under the gradient. Okay, so and this one or that one? Yes. That one is total density at the moment R and T, and these are distribution for which kinetic equation is written, and N is the integral over the distribution over the energy. So all that is most conveniently to be analyzed in a spirit of what in physics of superconductor is called quasi-classical technique, which was developed first by Eilenberger and Larkin and Ovchinnikov. And what we did is to follow the same route as what it was in the superconductivity, but to apply it to Gross-Pitaevsky, or this nonlinearity equation, and after that to write what will be the effective equation in the diffusive approximation. In case of superconductivity, that is done in what is called Uzadel equation, and technology which we apply is some element of between some nonlinear sigma model, Keldysh technique, etc., which I will not speak. More specifically, we follow this kind of route of analyzing nonlinear equations, this Martin T.J. Rose technique, but not exactly, because we do not have external source which I use in this technique, but we have just something which we average over realization of disorder, and then eventually somehow proceed in a similar manner. And the other thing is to apply in this technology this quasi-classical approximation. Okay, anyway, most important here is that we assume two major inequality, namely we assume that disorder is relatively weak, namely that typical energy of, so to say, particle from what the wave packet is created is larger than the strength of disorder. The other thing is that we assume that we are working with the relatively large cloud, which will be of size will be larger than the scattering length, and that's why we may assume some standard assumption about which are gradient expansion. Okay, so that is this equation. So, and that's Shmuel, your answer to your question. And all that is moving in this self-consistent potential, which is created by non-linearity, and that is what is the initial distribution, which is sitting here. And it is clear that one should simplify things, namely that since you are moving in this potential which is created by non-linearity, then what is convenient is to shift your energy in such a way that that's what you stand now, that instead of energy to use kinetic energy, just because diffusion will then depend on the kinetic energy. So that is a big picture of what is going on. This wave packet just create potential and moving in the presence of disorder in the self-consistent potential created by itself. After shift, it will be energy minus the it's up to you, but let us assume that simplest version when it is proportional to energy. V square over tau, V square is energy.
Approximations that were introduced here, and how will they look, say, asymptotically in some limit?
Approximation is, as I say, that you have that yours just phase which correspond to the energies, rapidness of oscillation of phase from what you did all this is such that wavelength is shorter than the mean free path. In other words, disorder is weak, but the cloud is large, and that's why it is standard approximation which allow to use to apply the gradient expansion in the analyzing of kinetic equation. Okay, so here it is what you will get after shift. That is appears to be this equation. Now, and in order to get some idea what it is about, let us integrate our energy, and then you will get this kind of non-linear equation, which is of course misleading because that kind of thing is just nothing. It is something which itself should be defined. It is average per particle, just which one have, and it's itself should be defined from that. But it gives provide you with certain hints that actually it is equation for non-linear diffusion, and this coefficient of this non-linear diffusion is that the just kinetic energy plus, in case when I say the diffusion will be v square over tau, and something which is originate from non-linearity. So
if the cloud is expanding, then you will have basically n going to 0 in the nonlinear equation because normalization is preserved, and the diffusion coefficient should also go to 0 because you have Anderson localization. Same way if we do it in 1 or 2 dimensions.
So what?
So okay, so this is what you mean. So you will expect from this theory that.
Let's postpone this up to the talk.
Okay?
Let's postpone this up to the talk. Meanwhile, I didn't say anything in the how this equation is dealing with Anderson localization.
Okay.
So far, there is just diffusion, and what I'm trying to say that non-linearity is influence this process. That there are lots of interesting things before diffusion happened because of just interplay between the diffusion and non-linearity. Okay. So they say that if one have neglect that one, then you have this nonlinear diffusion, and that is famous Zeldovich-Kompany's equation, porous medium. And there is famous solution, which is Baron-Blatt solution. And for this case, one have known what is going on, namely that radius just expand more rapidly than linear. T1 square root in that sense is more rapid than linear. So we have some kind of explosion, and which of course why these people were interested in this equation. And actually one may think that maybe something like that will be here, and it is not the case, because it was we unintentionally derived something which may be called Talanov theorem, which is known in the nonlinear, but now in the presence of disorder. Namely, one can connect the rate of expansion of the cloud in time, this R square average, how it's dependent on time, and it's appeared to be that in this system there is one more conserving property apart from the number of particles, namely energy is conserved. And in 2 dimensions only, it's appeared to be that in this case one may connect the rate of expansion with the coefficient of diffusion with energy which corresponds to the average particle energy of per particle. So despite that this nonlinear part attempts to lead to the explosion, actually picture in this diffusion case appear to be more complicated, and there are no explosions, but just ordinary kind of expansion diffusive life with this rate. But it's possible to prove this kind of connection between the square radius on the energy conservation only in case of 2 dimensions. So log explosion was what I say, that one may think that in the center you have something when you may neglect this kinetic energy and only nonlinearity treat will be a sort of explosion, while on something which is going here where density is small, most important will be gradient part, and that's why you have something which lock this explosion, and there is something which combination of the 2 phenomena in such a way, nevertheless, that to obey this formula. Okay, now in case of attraction, one may have 2 signs. One is positive and negative, depending on how strong is nonlinearity. And just in case when this one is positive, one still have expansion, and one have negative, it is repulsion. But one may see from the studies of what is known about this equation, that actually what one may expect, that in case of attraction, since it's to a certain extent correspond to the changing of the direction of time, if the explosion solution was absolutely stable, that means that this, for the case of attraction, solution will be unstable most probably. And that's why most what one may expect is a sort of fragmentation of your initial cloud on some pieces which presumably behave in a different way. So most probably fast particle will run away, and slow one will give some fragment. Okay, this is not yet conclusion, but basically that is what was done so far. Namely, there was a set of equations which was derived assuming that you have some evolution of wave packet on large distances in random scattering and nonlinearity. And what I tell was analysis of this equation, just never mind whether it is how it is just actually related to the initial problem. And we found out that there can, apart from Anderson localization, there can be some other interesting phenomenon in the diffusive regime, just which I described. Why I'm saying that, never mind whether it is related or not, because so far we didn't discuss anything about collision. And it is classical equation, but collision exists in classical physics as well. And the usual way to study effect of collision is something like what, for example, is described in the book of Zakharov, Lvov, and Falkovich. And it is done in the following way, that one writes an equation for the propagation of density, and then non-linearity leads to the higher term, and then this higher term is decoupled following the random phase approximation. And in this way, one gets an equation which is interpreted as collision, and one can find collision integral. Since we work with some field theoretical technique, it appears to be that one can reproduce this kind of collision terms straightforwardly just by taking the action, taking this interaction term in the second order, and to calculate in calculation of the second order the propagator using the solution of the previous problem. Okay, then there are three contributions, which are just one is the equivalent of something like Keldysh component in the regular technique, which is give you information about what is going on with the population, with occupation, and the other two contributions which are just describing what is going on with your particles. And so here it is what is coming out. And collision integral can be found in a standard way if one finds these two. And that is a collision integral, which one can immediately see that it is what one will have for the standard. That's exactly what people in nonlinear physics obtain. And comparing, for example, with Bose particles, not with the Gross-Pitaevsky, but with the Bose particles, one can see that if one neglect in the occupation number this one, with this Bose statistics, and use classical one, then it is something which corresponds to the collision term 2 into 2 in the kinetic theory of Bose gases. So that is what you have. Now, since it is a term which is derived from the classical equation, it doesn't depend on microscopy, and it is the same term both for the nonlinear Schrödinger and for Gross-Pitaevsky equation. Now, again, so what we are doing? We are interested in physics on large scale. We assume that the size of the cloud is much larger than the scattering length due to the impurity, which in turn is much larger than the wavelength. And we are not interested in microscopic, and if would be interested, then one may say that this wavelength should be, in case of the boson atoms, is much larger than interparticle distances, which in turn is larger than the scattering length. And this is how this nonlinearity is related to the scattering length. So if one take estimate of this collision rate, and it is the same as to say that it is the quasi-particle lifetime, then one will get that this lifetime is given by that one. That is done on the assumption that one have the distribution in energy which is comparable with energy itself. Then that is the rate. And one sees that if you have a case when the energy is and the nonlinearity are comparable, then the estimate for the lifetime is such that it is actually of the order of energy, which is supposed to be much larger than the mean-free time. So, in other words, in this case, one have transition from the diffusion regime to a sort of from collisionless to a sort of some just hydrodynamical regime. And the difference is that in the previous, what I was telling is neglecting collision, one have to study each component of the kinetic equation independently and then to sum the result. While here, in the case of rapid collision, one have studied how all them mixing together because of the rapid collision when you are in this regime, which is, of course, would be most interesting. Okay, now a few, this is the last slide, I guess, here. So that is how all that is related maybe for localization. So Bose-Gas just where this kind of thing is observed. So namely, in principle, one may be in situation when the size of the cloud needed for localization will be such that if one calculates what will be the density which correspond to the radius of localization, that is for the case of 2D, that is thickness D, and L is this radius of localization. So that is the density, and if one takes this rate which was calculated and takes this density, in principle one may be in situation when this rate is larger than the tau-less energy. And if you remember the initial way, the first thing in discussing of localization is comparison between the tau-less energy and level spacing. And if tau-less energy is larger than level spacing, then it is conducting, and if tau-less energy is smaller, then it is insulating. So what I'm talking about that in principle one can be if your number of particles initially in your cloud and disorder are such that what you're supposed to have for the density on the radius of localization will be such that this rate of collision will be larger than the tau-less energy, then standard criterion for localization will not work at all. And this scale will be not noticed at all because there is much more important scale of rapid collisions. Now, even when you have opposite case, when you are in situation when the tau-less energy takes over, so you have that these collisions are random, then still what happened in this kind of problem is that there is some distribution of energy and which are in this place. So in other words, you will end with something like effective temperature because of this distribution of energy. And there are questions about how all that is equilibrized and in what energy part of the spectrum all this equilibration happens, etc. But in any case, even in this case, one may speak about something like hopping and so on, even when you are looking to be in situation favoring Anderson localization. Now, and that's what I say, that you may have just situation when the rate of equilibration is important and so on. So what I'm talking about is that actually in this kind of physics there are much more rich phenomena than just to talk about Anderson localization alone, because non-linearity leads to quite rich amount of other phenomena. Now finally, okay, that was done together with Georg Schwitter. Paper about role of collision is in preparation. Thank you for your attention, and my warmest regards to Leonid in his birthday. And usually the wish in this kind of situation is till 120, so I wish him till 120 after the Anderson localization. Thank you for your attention.
My question is the following. Your technique, so first of all, quasi-Zadel equation and also collision integral calculations, are they limited to large enough dimensions, or they apply also in 1D?
No, strictly.
I mean, 1 plus 1, time and space.
Strictly speaking, of course not, but you may think about what will be in case when you have a sort of tube. Then such thing can be applicable. So when you are speaking about something which a la Berezinski, of course not.
Okay.
But if you will take something
Okay, and then,
a la Dorokhov with
okay.
many channels and so on.
Okay. If yes, then what is the qualitative difference in the time T star in different dimensions? So we know that when there is interaction, then T star behaves differently as a function of temperature in different dimensions. Here it should behave differently as a function of the total energy. So is there any idea?
Okay. This estimate which I'm talking about, it is assuming that it is not like what you do know in case of the Fermion disorder system, when this 1 over tau disorder is influence of all that and so on. Here, what happens is that convergence of all that is on small scales of the order, just because your wavelength is of quite different scale and so on, and collision happen because of the scattering. So in other words, disorder and all this kind of thing what you have in mind doesn't matter, and what does matter it is like in case, I would say, Fermi liquid and so, where you do know that the answer does not depend on dimension. So this estimate is for that kind of.
So it is much less dimension dependent than
this estimate is
in the usual case. Because you don't have separation of the length scales like P Fermi and the other.
Exactly. There are no such thing like what you're talking about, that what is going on here, that these collisions happen. There are no Fermi surfaces, and that's why collision and all that is determined by small scale, where disorder is not important. And after that, similar to what you have to do. Yes, me. Yes, right.
Yeah, I remember that in one dimension there is a rigorous result by Weizmann and Walser for effects of interactions. And the claim is that there will be still dynamical localization with interactions. I don't remember the conditions. Can you comment on this, or someone, if someone remembers?
I cannot comment, but again, it is definitely.
I don't think it's relevant here.
It is definitely not about one dimension per se. It is at best, when you consider macroscopically, some one-dimensional just variation. So in other words, there are no just like what you have backward scattering to and back and so on. So that is only when you are talking about some diffusion, which is macroscopically, after that will be considered in 1D. So in other words, it is some tube. I don't think that.
Okay, I think we'll hold further questions for during the break. Thank you very much.